So in the previous screencast, we showed that when we're thinking about a synthesis that requires carrying out successive electrophilic aromatic substitution reactions, the order in which ortho, para, and meta-directing groups are added to the ring can impact whether the synthesis is successful. With this in mind, we're going to revisit some reactions that we looked at in chapter 24 that can be used to interconvert ortho, para, and meta-directing substituents. So that means the regiochemistry of a substitution that takes place later in the synthesis is not automatically predetermined by the ortho, para, or meta-directing ability of the substituent added earlier. So remember from chapter 24, for example, that treating the alkyl benzene with a hot basic solution of potassium permanganate yields benzoic acid once you do an acid workup. The substituent in the reactant here is an alkyl group, and remember that's an ortho-para director. But the substituent produced is a CO2 group, which is a meta-director. And so when we start to think about this, one of the questions we can ask ourselves is, how can we use this reaction in the synthesis of p-nitrobenzoic acid from benzene? And so we see that synthesis here. Now, the CO2 substituent and the NO2 substituent are both meta-directors, but the desired product is a para-isomer. What we can do is we can work around this problem by making sure that the second substituent is added after an ortho-para is already on the ring, such as the alkyl group. So, when we look here, and we're kind of thinking backwards, we can undo the oxidation, right? Undo a nitration, and then we undo the alkylation. And so kind of, sometimes this for me is easier to think in the forward direction, which is, look, we leave that R group on there, right, which is an ortho-para director. We nitrate it, right, so that goes on in the para position, and then we do the reaction with KMNO4 to get the carboxylic acid group here. So we keep the R group on for its ortho-para directing functionality and then save this reaction to the end where now it becomes a meta-director. So if you like puzzles, this is really for you because it's kind of like a big puzzle. Now, we can even achieve greater flexibility in synthesis with the ability to convert a meta-director into an ortho-para director. We've already encountered two types of reductions to accomplish this. One that we talked about in chapter 24 is the reduction of a nitro group to an amine group. Ooh, I don't know why. I apparently am having problems here. Okay, there we go. I couldn't handle it being off to the side. Right, okay, so like I was saying, we have a reduction of a nitro group to an amine group, okay? And then the second is a reduction of a carbonyl group on a ketone or aldehyde to a methylene group. And that carbonyl reduction can be done in either acidic conditions with the Clemmensen reduction or basic conditions with Wolff-Kishner or neutral conditions with the Raney-Nickel reduction. The utility of these reactions is demonstrated in this reaction when M-bromoethylbenzene is synthesized from benzene. The substituents here are meta to each other, right? And so what that means is the second of the two electrophilic aromatic substitution reactions needs to be carried out with a meta-director already on the ring. The problem, of course, is that both the bromine and the CH2CH3, or what we would consider just a generic R, are ortho-para directors. So what we have to do is add a meta-director, right, and then do an additional reaction to convert to one of these two groups. So when we think about this, we say, okay, how can we do a conversion to one of these two groups from something that's a meta-director? Well, if we undo a reduction here, that leaves us the carbonyl group, which is a meta-director. And so then we can undo the bromination and undo the acylation. So we put the acyl group on first. That's going to meta-direct the bromine here. Then we reduce this HCl and then the zinc mercury mixture, and that reduces that to a CH2 here. So we can kind of, with organic synthesis, right, we can do some pretty savvy things. Now, another thing that also falls here are protecting groups. I mentioned in class that when I did organic synthesis, we used quite a few protecting groups, mostly because we were doing peptide synthesis, right? And so there are two ways to incorporate a protecting group into an aromatic substitution reaction. One is to temporarily lower the reactivity of a substituent attached to the ring by reversibly converting it to a different functional group. And then the second is to block a particular site on the ring where the substituent is not, or the substitution is not desired. So if we look at kind of that first scenario, the question you might ask yourself is, how can we carry out the transformation where aniline here is acylated in the para position here? So we've added an acyl group, the C double bond O with the R group here. So if we did a Friedel-Crafts, right, given that a NH2 is an orthopara director, what we're going to find is this is not feasible, okay, because we're going to form a complex here, and it deactivates that Friedel-Crafts, so it makes it impossible. And remember that reason again is that the NH2 is a good Lewis base and AlCl3 is a strong Lewis acid, and so they react with each other. So to avoid this problem, we can convert the amino group temporarily to a different functional group that maybe wouldn't react. So look at this, right? What you do is you take this amino group here, right, and you convert it to an amide. And amides are really unreactive in these types of syntheses. So then you can come along and do the Friedel-Crafts reaction here because that amide is protecting the amine. So you do the Friedel-Crafts reaction, you attach the acyl group, you do an amide hydrolysis reaction, and you've got your amine back. That's a very, very effective, very nice synthesis with protecting groups. Now, in some instances, the reaction we want to carry out leads to possible substitution at 2 or more sites on the ring. This demonstrates the second use of protecting groups in electrophilic aromatic substitution, namely, we can guide the regiochemistry by protecting one of those sites. So, for example, let's think about how you would carry out this reaction. You want to get the ortho product, but not the para. So is there a way that you can kind of guide this reaction to just get the ortho? So the OH group is an orthopara director, right? So if you were to do direct bromination, you would get both of the isomers. However, what you can do is you can use a sulfonyl group, which can block the reactivity of the para position. Then you can do the bromination and just get reactions in the ortho position. Then you go through a deprotection step and remove the SO3H. And so we do this with water and sulfuric acid. So in organic synthesis, you can use a lot of things as protecting groups. Another thing that can be used a lot of time here that we can see is when we look at the NH2 here, that's a strongly activating group. We can convert it to an amide, and that's going to prevent overhalogenation, right? So you're only going to get one halogenation. And then in the second step, right, the halogenation takes place ortho to this amide group. That's an orthopara director. And so, and remember, this is also more activating than this, okay? So there, it's going to be orthopara. And then what you'll do is you'll deprotect the NH2 group using hydrolysis, and then you would treat it with a diazo group here, and you can convert, right, with an H3PO2 back to a hydrogen group. So even though the NH2 group was not in the final product, we used it as a protecting group because we could take it and turn it into an amide and then remove the amide to get us back to the hydrogen. So a lot of times NH2 here would be considered a blocking group.